All right. Breadth first search. So breadth first search, as we discussed, is an algorithm to traverse a graph. So traversal means that you visit all the edges and you visit all the vertices. And breadth first search is a technique to solve many graph problems. Okay. So remember that, just to go recall some definitions, a vertex V is connected. If U is connected to V, if there's a path between U and V, let us just think about undirected graphs, simple undirected graphs for now. Okay, and there's a very important concept of the shortest path distance, which I denote as dist UV, which is the length in edges of the shortest path between U and V. There can be many paths between U and V. The length of the shortest path is called dist UV. Okay, so what is BFS of S? BFS of S takes a single argument, which is the source vertex. This is a procedure that takes a single argument, and what it outputs is something called a shortest path tree rooted at S. So what is a shortest path tree? So it is a tree, not a binary tree. So don't think of there being any invariance, just like, some conditions on the nodes. It's just a tree. And I hope everyone can hear me. There's some disturbance outside, but can everyone hear me clearly? Yeah? Okay.
Loud and clear.
Okay, good. So benefits of having an external microphone. So in this tree, the root is S, and all the vertices that are connected to S are going to be in this tree. What this means is if you look at the graph and you look at all the vertices that have a path to S, they're going to lie somewhere in this tree. Furthermore, for any vertex in the tree, if you take the path from V to the root by going up, just follow the parents, then that path is a shortest path. These are the conditions of a shortest path tree. And so what BFS outputs is a shortest path tree as follows. So BFS maintains two arrays. There's predecessor and visited. So the predecessor array is really like the parent pointers of the tree. So, and you'll see why it's called predecessor. The predecessor of V is the parent of V in the shortest path tree. Initially, it's all set to null. So initially, you don't have any tree. Visited is a Boolean array indexed. So both of these arrays are indexed by V, which we assume goes from 1 to n. Visited is going to be true if BFS visits V, false otherwise. Okay, so let's just walk over the code for breadth first search. So the code for breadth first search goes as follows. You initialize a queue. That's capital Q with S in the queue. So S is going to be in the queue. Predecessor is all initialized to null. Visited is going to be all false. Except for visited S, which we set to true. Because we're saying that we start the BFS from S, S is visited. Now, while the queue is non-empty, we're going to remove what's on the top of the queue, dequeue it. Then for every V that is in the neighborhood, if V has not been visited before, visited V is false, we visit it, meaning that we set it to true. We make the predecessor of V U. What this means is that we discovered V through U. And so that means that that edge, UV, was the one that discovered V, and hence that edge is going to be in the shortest path tree. The predecessor of V is U, and then we add V to the queue. And we just keep doing this process until the queue is non-empty. Okay? So maybe this is not clear why this works, but are there any questions about this code itself? Any questions?
Yeah. So I had a question. If
Yes.
the keys aren't actual integers that can be indexed in an array, would something like a hash table be used? So if
You mean if they were not integers?
yeah, if they're not integers. And
So
you can,
typically what you would do is that you could use a map of those vertices to 1 to n. Does that make sense? You would just have
Yeah.
you could just, and then you would just, it's like relabel them from 1 to n. That is usually the way of doing it. But you could naturally maintain all of these as hash tables directly. In this case, it's almost like this is maintained as a bitmap, but you can also maintain it as a hash table. Exactly. Someone else has their hand raised.
So for the neighbor adjacency list, for the data structure of that, would it be recommended to do like a linked list or just like an array?
Oh, for storing the adjacency list,
Yeah.
it doesn't really matter. So conventionally, people would not use an array; they would use a linked list. But in your implementations, you could just use, you could even use like a hash map for that, or a set data structure, like anything in C++ which is convenient. Because the issue with having like a list is that, searching for things is a little harder. Like you have to traverse the list, so you could store it actually as a hash table. But conventionally, people will store it as a list. Okay. Any questions? Okay, so let me, the best way of understanding this procedure is to actually see a visualization of how BFS runs. Okay, so any questions? Okay, good. I'll just go over the chat again. All right. So actually, sorry, before I continue, let me write down, formally speaking, what is the guarantee of BFS, right? So what is the guarantee of BFS? And I kind of wrote this in the shortest path tree, but I want to write this again. So this is a guarantee, meaning that one can mathematically prove this, that when BFS S terminates. So when the procedure terminates, the following hold for all vertices in V, right? So we're looking at the entire graph. This is the entire graph. For all the vertices in the graph, visited of V is true if and only if S is connected to V, meaning that you could have vertices that don't have connections to S, right? So G could be like this collection of different components, as they call it, and this would be S. And so all the vertices in here are connected to S, and those are the only ones where visited V will be true. Just to sort of complete this, predecessor V is null if and only if V is equal to S or V is not connected to S. So BFS starting from S can never visit these vertices, and so their predecessor in visited will just remain to be false. Now note that the predecessor of S is always going to be null. Thirdly, for V connected to S, the vertices V, the predecessor of V, the predecessor of the predecessor of V, so on and so forth, all the way going back to S, these vertices form a shortest path in reverse from S to V. Okay? So I've just rewritten what the properties of a shortest path tree are, but kind of broken it up in terms of the predecessor pointers, right? So when BFS terminates, so when BFS finally finishes, what that means is when this while loop finishes, so it's doing a bunch of things. Instead of having like just a simple return value, it's actually returning an entire data structure. It's actually returning these predecessor and visited arrays, and you have guarantees on what these arrays are when you finish them, Okay? So what are these guarantees? Firstly, visited of V is true if S is connected to V, if and only if. What this means, if visited of V is true, then S is connected to V. If visited of V is false, then S is not connected to V. The predecessor is null if and only if V is equal to S or V is not connected to S. Finally, for V connected to S, the vertices V, predecessor of V, predecessor of the predecessor of V, so on and so forth, form a shortest path. This path over here is precisely, excuse me, this path, because the predecessor is like a parent pointer. And so it's exactly that. Okay? All right, so any questions about what I've written here? All right, if not, then yes.
One question.
Yes.
So the original graph itself, is that stored in like an array, or is this graph kind of like a bunch of pointers?
The graph is stored as an adjacency list. So if you recall,
Okay, so this is all list. It's like a heap. We're just pretending there's like structure.
No. So we are not mucking with the actual graph itself. We're not changing the graph here.
Yeah.
We are only constructing these new arrays. The graph remains where it is.
Yeah.
None of the pointers that constitute the graph are being changed.
Oh, okay, but the original graph is made of pointers, though.
The original graph is made of pointers, just like everything in the world is made of bits, right? So everything is stored somewhere or the other. The graph is stored as an adjacency list.
But our tree is made of lists or arrays.
The tree is stored as a collection of parent pointers. Let me give an example. Let me actually work out an example, and then it might be clear what's going on. I'm going to work this example out, and then you can ask me more questions. Okay, so I'm just going to use this visualization. Hang on a second. Okay, does everyone see my screen? Yes?
Yes.
Good. Okay, so you should see that there is this graph drawn over here with 8 vertices, numbered from it's numbered 0 to 7 and not 1 to 8. But you see this graph that's drawn here, and it's represented as an adjacency list. So this is what's called a logical representation, meaning this is like a pictorial representation. As an adjacency list, this is what the graph looks like. So just to go back a bit, if excuse me, 0 is connected to vertices 1 and 3, then in the adjacency list representation, it's connected to 1 and 3. I think ignore the second ones. Those are like weights. So ignore what the weights are. Just look at the stuff in blue. So 0 is connected to 1 and 3. 1 is connected to 0 and 5. 2 has a neighbor of 4 and 5. 5 has a neighbor of 1, 2, 3, 7. And so it's the same over here. 5 has neighbors 1, 2, 3, 7. Now, in the viz, it's sorted, but it doesn't have to be sorted in general. Okay, so, and what are these? You have parent pointers. Initially, all of these are null. And you have this visited array, all of which is false to begin with. Okay, any questions about this? Does this make sense? All right, let us proceed. Excuse me. So let's pick a vertex and let's start BFS. So maybe let's start from vertex 4. Okay? Now I'm going to run the BFS. Now what is going to happen? Okay, so let's see if I could. Sorry. Okay, so what happened here is, okay, let's just step back a second. So it starts at vertex 4. Now look, the BFS queue has 4 in it. That's the initialization. Okay? Then what it does is it says, let me look at all the neighbors of 4, right? So if you go back to the procedure, remember that there's 4 is in the queue, is looking at the head of the queue, and it's looking at the neighbor. So it looks at its first neighbor, whatever that is, and that happens to be 2. So in the adjacency matrix representation, it's looking at that first block over there. In terms of the graph, it's looking at that. And so it's looking at 2 and it's saying, hey, is 2 visited or not? And so 2 is not visited. So it's going to visit 2, and then it's going to add 2 to the queue and make the parent of 2 be 4. Yeah, someone raised their hand. Go ahead.
Wait, so shouldn't we not set, in this case, 4? So the one Sorry, let me explain better. It says we should set visited S as true.
Visited for, yeah. So it should be setting visited for as true, and I think this doesn't do it. But you can like
Okay, but wouldn't that ignore 4?
it would ignore for. So I think that's just like sort of an error in the viz.
Okay.
You're absolutely right. This should be set to true, and it doesn't do. The viz doesn't do that.
Okay.
Yeah. Okay. So good. So now what happened is visited of 2 is set to true, and the predecessor of 2 is 4. So that predecessor is marked as this directed arrow. So think of this directed arrow simply means that the predecessor of 2 is 4. So the blue arrows are going to become the BFS tree, and note the 2 is now sitting in the queue. Okay, so now let's look at the next one. So 4 is going to visit 7. Like we're going to traverse that neighbor, and so 7 is visited. So then 7 becomes true. The predecessor of 7 is 4, and so this edge is marked in blue. The marking in blue, you shouldn't think of the graph as being changed. It's just helping you represent what is happening in this picture. Okay, so now the BFS queue has 4, 2, 7. So 4 is actually DQ. That's why it's in blue. It's like that's what's colored. Someone raise their hand. Go ahead.
Was it visit 2 first because of the fact that it's closer than 7?
Good question. So closer in what sense?
Just purely looking at the graph. I don't
No,
know how
so
to explain it.
The geometry of what you see is irrelevant. So this is just a way to represent things. In memory, this is stored in some way. So it's a good question. Why did it go to 2 before 7? Because if you go to the adjacency list, 2 appears before 7.
Oh, okay.
If
I see.
the adjacency list had 7 before 2, then it would see 7 first.
Got it.
And it has nothing to do with proximity in terms of what is drawn, nor does it have anything to do with the actual sorting of the labels or anything like that. It so happens that in this case, this gentleman who implemented it sorted it in his visualization, but that is not necessarily true. So it just depends on what the order is. Does that make sense? I want to make that very clear.
Yeah, makes sense.
Okay, good. So now what has happened is that you look at the BFS queue, 4, 2, 7. So actually 4 is being considered, so it's being DQ'd. 2 and 7 are in the queue now. Okay, so now let's go one step forward. Let me just step forward. So I think that, so sorry. Okay, so I think, yeah, let me explain that again. So let's step back a bit. Okay, look at the queue now. In the next step, 4 is now finished. So if we step forward, what's happening is that 2 is at the beginning of the queue. So whatever is in blue is being considered. Now, why is this edge being marked? So what it's saying is we're looking at 2's adjacency list because we're considering 2. And we're looking at the first thing in 2, which is 4. Okay. Now, technically, there's an error here. This has to be marked true. This is visited, and it's not there in the viz. So there's a little bug in the viz that this is not marked true. But actually, this is true, and so it's going to ignore that edge. Remember, when it's traversing the adjacency list, if anything is already visited, it moves on to the next one without doing anything. Okay, so that's what's going to happen here. So it's already seen 4. Now that is not marked here as someone pointed out. So that's an error in the viz, but actually the underlying code is correct. Okay, so good. So now it's going to move to the next neighbor, and the next neighbor happens to be 5. So we're looking at 2. Remember, that's the BFS queue. We look at 5. 5 is not visited. 5 is not visited. So it's going to set 5 to be true. It's visited. And the predecessor of 5 is now 2. Okay? Now observe that if you look at the path from 5 to 4, which remember 4 was the source. If you follow those arrows backwards, you end up, this is actually a shortest path. This is a shortest path. Okay? And this is really important. Now, so 2 is actually going to be done. Now, what is the next vertex to be visited? 7. Now, let's see what happens when you do 7. Now, this is interesting. So we're looking at 7, right? So let's go to the adjacency list representation. We're looking at 7. 7 has 2 neighbors, 4 and 5. So 7 is going to look at 4. Now 4 is already visited, although this is marked false. It was a source and that's a bug here, right? So this should have been true. So 4 is already visited, so nothing to do there. Then it visits 5, but 5 is already visited, right? So there's nothing to do there. So essentially 7 is just going to exit from the queue without doing anything. And then we move on to 5. Excuse me. Now 5 is going to look at its neighbors. 5 has 4 neighbors, 1, 3, 2, and 7. Now observe that the predecessor of 1 and 3 is going to become 5. The parents of 1 and 3 are 5. So you're going to get more shortest paths. You're going to get the shortest path from 4 to 1 is going to be 4, 2, 5, 1. Even though there is a longer path that gets to 1. You could go 4, 2, 5, 3, 0, 1. But that long path is not going to be considered by BFS because BFS is doing this breadth first. As soon as it finds it, it says, okay, I've found the shortest path. So let's just step forward. So good. So then now 1 is visited. The predecessor of 5 is 1. Let's do it again. So so one of the neighbors of 5 is 2, but 2 has already been visited. Nothing to do there. 3 has not been visited. So go ahead and make 3 visited. The predecessor of 3 is now 5. Right? The predecessor of 3 is 5. That's what's marked here. 7 is already visited. There's nothing to do there. So at this point, 5 is going to exit from the queue, and 1 and 3 are going to be in the queue. Okay? And now we're looking at the queue again. So now we start from 1. And so 1 is going to visit 0. Okay? Does this make sense? Now observe. So this is saying that 1 is going to now look at 5, but then 5 is already visited. And that's that. And so that basically ends, well, okay, so then, 3 is still in the queue. And 3 is going to visit 0, but then 0 has already been visited. 3 is going to look at 5, but 5 has already been visited. Finally, it's going to go to 0. 0 is going to look at its neighbors 1. 1 is already visited. From 0, 3 is already visited. And so essentially what happens is at this point is that the queue becomes empty. Okay, the animation is complete. The queue is empty. Note that there are 2 vertices which don't have parent pointers. There's the vertex 6, which never got visited. And there's the vertex 4, which is the source. If you look at the visited array, again, like this entry here is a bug. It should be true. But 6 is still false because 6 has not been visited. So this is a small visualization of BFS. Does this make sense? Any questions at this point? I hope this helps.
One question.
Yes, go ahead.
Oh, sorry, go ahead.
I was just going to say it's a lossy transformation. You can't reproduce the original graph from the tree.
Good. That's a good question. So the tree is necessarily a subgraph, meaning that there are certain edges in the graph which are not present in the BFS tree. It's instead of thinking of it as a transformation, it's more like it is a traversal of the graph. And the traversal gives you some information. Now, if you did what's called a depth-first traversal, you get a different set of edges. And you kind of look at these edges to deduce various things about the graph. Yeah, someone else had a question.
So yeah, in this example, it's
Yes.
very convenient that all of the numbers are sequential from 0 to 7. I'm assuming that in real life that these indexes are different than the data of the nodes, or there's a
Yeah, exactly. So as someone had asked, I mean, you could actually, instead of storing this as an adjacency list, you could store this as any other kind of like a hash map or something. So instead of having an array of lists, you could have a hash map of lists. You could have a hash table of lists, meaning that as long as you can retrieve the neighbors of a vertex, you're in good shape. Does that make sense?
Yeah, I guess I was wondering, how do we assign indexes to a graph? Or we don't really need to do that?
You don't need to do that. You're going to have to figure that out for homework 4. I'm going to give you a
joy.
graph for homework 4, and you have to kind of figure out how you're going to represent all of this in data. You're right that it's not obvious. Yeah, go on.
If I were to use a hash table for the adjacency list, or whichever one you just showed, would I also want to use a hash table for the parent and for the visited also?
Yep.
Okay, cool.
Someone asked, this is an undirected graph? Yes, this is an undirected graph. The direction of the arrows is representing the parent. The parents, of course, have a sense of direction, right? I mean, if 0, in this case, 1 is a parent of 0, doesn't mean that 0 is a parent of 1. But these are parents in the shortest path tree, and the shortest path tree is specifically from 4. This does not give you shortest path information from, let's say, 0 to 3. What is the shortest path from 0 to 3? It's just that one edge. The distance of 0 to 3 is 1. But if you were to use the tree, there are 3, there's like a path of length 3. Right? So this only gives you the shortest path information from 4. Any questions about that? Any questions about that? So does this make sense? Okay. So I'm going to stop my share now. Hopefully that helps. Hopefully now you can kind of understand, you have a better sense. Like, you have to sort of play around with this a little bit more. BFS it's a simple code, but rather it's pretty intricate as to why it works the way it works. Okay? All right. So and so I believe that I think I've already released homework 4. So please go and read homework 4 now. And homework 4 is really all about doing breadth first search. Okay? It's all about doing breadth first search. Now, before I want to say a few things about breadth first search and its running time. So this is BFS from a single source. What does breadth first search on the entire graph mean? So it's actually pretty straightforward. Once you have breadth first search on G, it basically just has these steps. So it's the first step is, of course, for all vertices V, initialize predecessor of V is null, and visited of V is false. And then what we do is, quite simply, we say for all vertices in V, if visited of V is false, then you run BFS from V. Okay, does this make sense? So think about what happens in this example over here. Initially, everything is unvisited, it's not visited. We're going to pick some vertex in here. And this and we're going to call BFS from this vertex. I'm going to call this vertex, let me call it V1. And BFS from V1 is going to visit all the vertices in here. But these vertices are still unvisited. So then in this loop, as it keeps going through this loop, if it ever touches a vertex in here, it doesn't do anything. It's just going to return. But once it hits one vertex here, then it's going to visit all of these vertices. And eventually it's going to look at a vertex there, visit all of those, so on and so forth. Is this clear? So in the end, all the vertices are visited. All the vertices are visited. So someone said, will the predecessor array be changed each time you call BFS? Exactly. So think of this, the predecessor and visitor are like global variables for that procedure. This is global with respect to this, right? So every time you run BFS, certain predecessors and visited are going to be changes. So someone has their hand up, go ahead and lower your hand and ask. Yes?
Yeah, so is V1 then just kind of arbitrarily picked from the graph?
Good question. V1 is arbitrarily picked according to the ordering of your for loop,
Okay.
right? So it depends on what your for loop is going to do in terms of its ordering. Does that make sense?
Yeah, it makes sense.
Yeah, okay. So what is the output then? So we know that in the end, all the vertices are going to be visited, so all the visited are going to be true. What is the predecessor array going to look like? What does it give you? Any thoughts? What that is? So it's all the nodes that have ever been visited. But what? Right. But so remember that when you call BFS of S, the predecessor array represents a tree. Okay? So let me ask you a question here. In the end, the predecessor array, so I guess that's my question, represents what? Is it a single tree? Many trees? Is it not a tree?
Wouldn't it represent one or more trees?
Okay, good, good. So in this graph, how many trees would it represent?
4.
4 trees. For each of these blobs, you get 1 tree. So good. So essentially what predecessor represents, someone let me write this down. Predecessor represents a collection of trees. What do you call a collection of trees? Well,
A forest.
forest, exactly. This is called a forest. I suppose you could also call it an orchard, but for some reason in graph theory, people call it a forest. So what you get is, if you look at G, each of these blobs is called a connected component. So what is a connected component? It means that all pairs in the component, which is just a set, are connected. The story becomes a lot more complicated when the graph is directed. So let's just assume the graph is undirected. So when it's undirected, a connected component is just a set of vertices where all pairs in this set are connected to each other. Right? And for each connected component, for each connected component, there is a separate tree consisting of all vertices of that component. Right, so if you look at the output of BFS, you're going to get 1 tree over here. You're going to get 1 tree for that, 1 for this, 1 for here, 1 for this, so on and so forth. So BFS of G can be used to compute all connected components. It's a very common use case for breadth first search, which is to be able to compute all the connected components of the graph. Now, BFS of S finds all shortest path distances from S. Right? So you see how BFS, by slightly modifying things, by changing things a little bit, can do lots of really cool things. And that's one of the big use cases of BFS, is the ability to do multiple things. And I'll give you more examples of this. But I hope this is clear. Any questions about this?
So like that, when you're doing a BFS on the entire graph, the reason why you're looping all through all vertices is to get those to touch those connected components, right?
Exactly. BFS is trying to visit all the vertices of the graph.
So you're not actually like doing it multiple times in one connected component, because when you call it on one vertice inside the component, it does it immediately for the entire thing, right?
So it doesn't call BFS for all vertices in the component. What it does is it visits all the vertices. And once it visits a vertex, it's never going to call BFS from it ever again.
Because it found at least one that was true or valid.
Essentially, yeah. Well, one way to think of it is that you remember that visited array that just kept becoming true. Once a vertex is true, BFS never goes back to that vertex.
Yeah.
Right? And so that ensures that it never does the same crawl over and over again.
Okay. That makes sense.
Yeah, so someone said, I think they understand, but what is G then? So G again is the graph. So remember, G is like an adjacency list that you're provided. Now, this picture, it's obvious what the connected components are. But if I gave you the adjacency list, like adjacency list would just say, okay, vertex, 1, 2, 3, 4, so it's just a list over here. And if you look at this list, how do you know what all of these components are? Your code only has access to this list. From the list, you want to kind of reconstruct this picture. This logical picture that is drawn should not confuse you. This is just like, what I've drawn here is a logical picture. It's a logical representation. It's like a description of the linked list. I mean, what's stored in memory is just a collection of addresses and content. We use these pictures to visualize the algorithm. So I'm using this picture to visualize the algorithm as humans, you and I can do, but the code doesn't see this. The code basically, in some sense sees this, or it doesn't even see this. It just sees a bunch of pointers. It's using those pointers to follow through and construct what all the connected components are. Yes, is that clear? Any questions? Any questions? Someone said, do we need to reset the visited array each time? No, you cannot. You cannot reset the visited array every time you call this, because if you did, this would go in and this would never, you wouldn't get the right answer. Because if you reset, then what you've done is once you've visited a vertex, you'll go back and visit it again and do BFS. You don't want to do that. You want to do BFS only once in this blob over here. Excuse me. Is this clear? Any questions? Okay, good. So I want to say a few more things about BFS. What is the running time? That's a bit more complicated now. So let me just go back and show you the code. Let's look at BFS on G, right? BFS on the entire graph. Of course, we had this sort of complicated queuing, with this. So how do you make sense of the running time? It's a lot more complicated now. But if you think about it a little carefully, and you think about what I said about things being visited, you should be able to get some idea of what the running time is. So what is the running time parameterized by? There are two parameters. There's m, the number of edges, and n, the number of vertices. Remember, m is the number of edges, n is the number of vertices. And we'd like to parameterize the running time of BFS by m and n. And so how would you do that? What is it going to be? O of mn, m squared n, what?
I say it's just the sum of the two.
Why?
Because for each node, you kind of go look at, well, okay, the product of the two, because at each node you have to at least go look at all the neighbors.
Okay.
To see if they're visited already. And you do that at least once.
You do that at least once, right? So, but I argue that it's much better than the product. Okay, so let's go back. Okay, let me draw a picture. Okay, so good. So I think, so look at this adjacency list drawn as is. Remember, this is the adjacency list. Okay, here we have something more. So on and so forth. How many times do we go through this entire list? Question. How many times is this list traversed? Okay, question. I'm going to give you some options here. Red is just one time. Oh wait, I should say ABC because I have ABC. A is some O of 1, but potentially more than once. And C is, so let's just say this vertex is V. Is it going to be like the degree of V? This is the degree. Degree is the number of neighbors. So is it going to be, so you've got this graph here, right? This is some vertex. It's undirected. How many times are we going to traverse this entire list? Are we just going to traverse it once? Are we going to traverse it a constant number of times, but probably more than once? Or are we going to traverse it proportional to the degree? So I should probably say like O of that, theta of that. Meaning for every neighbor, we're going to have to traverse this entire list. So, okay, so what is, so I'll give you some, just launch this poll. Okay. Excuse me. Okay, so many people think that the answer, so it's actually, it's reasonably split, but by and large, the majority thinks that the number of times a list is traversed is O theta of D of V. But actually, you only traverse the list once. You only traverse it exactly one time. Okay?
Even if it's not directed?
Even if it is not directed, you traverse the list only once. Because, okay, so why? Let's look at this and see if we can figure that out. Right? Why is this list going to be traversed only once? When is the list traversed?
When it hasn't been visited.
But more generally, what is the step just before traversing the list? So we're traversing used list here. What is that operation? It's a DQ. So you traverse the list when you remove a vertex from the queue. Now, how many times can a vertex be in the queue? How many times can it be removed from the queue?
Once.
Exactly once, because you only insert it into the queue if it has not been visited. Right? If visited a vertex is false, then it goes into the queue. It's never going to go into the queue ever again. So every vertex goes into the queue exactly once. And in that time, its list gets traversed. I'm sorry, but when it gets DQ'd, its list is traversed. So I'll write this down, but I want to make sure that you understand the logic here. The adjacency list of a vertex is traversed when that vertex is removed from the queue. Now, a vertex enters the queue only once, and when it goes into the queue, visited becomes true. And that can only happen once because you never reset visited. Once visited becomes true, it's in the queue, and then when it exits the queue, when it gets DQ'd, its list gets traversed, and that's it. So it's traversed only once. Is this clear? Any questions? This is a good time to ask me. Okay, I'm just going to relaunch a poll saying, yes, I understand the logic. That is, I understand why the list is traversed once. A is yes, I understand. B is I don't understand. Okay, so most people aren't responding, but the ones who've responded, mostly an overwhelming majority understand. Again, if you don't understand, you should respond to the poll so that I get some feedback. Otherwise, it's very hard to judge.
So from a graph, from the list perspective, I kind of get it. From the graph perspective, it seems like you want to go look at all the things on the other line, on the other ends of the lines, or on the other ends of the edges as well.
So I'm sorry. So
if you look at a picture.
Okay, so let's look at. Let me draw a picture here. Okay, let's kind of. Okay, so here's my graph, and so I'm taking some vertex V here.
Right.
It's got some neighbors, right?
Sure.
Okay, so yeah, so now what are you saying?
So add another layer, maybe on one side, like add children
sure.
on one side,
So
maybe.
Like there are some more vertices.
Yeah, I think so.
Yeah. Okay. Good.
So
yes.
now you've gone from the center to like some far out place, like
Sure.
to the very edge there. Yeah, and so now you still have to go look back at the last two
These
neighbors to see they've already been visited, but you have to go check.
No, but then you will traverse this edge at most 2 times, one from this end, once from that end.
Oh, fair enough. Okay.
So the list, but then if you look at it from the perspective of the list, each list is traversed only once, and each edge is stored in 2 lists.
Okay, and you only, because the edge only has 2 endpoints, you can only get there twice
Precisely.
at the most. Okay,
Precisely.
cool.
Right? So actually, which is why I want to repeat, every adjacency list gets traversed exactly once. And this is, of course, for an undirected graph. For an undirected graph, every edge is present in 2 lists. Right? So if you look at this vertex, this edge xy, the edge is present in x's list and y's list, because if you look at the list corresponding to x, at some point somewhere down the line, you're going to have y. And if you look at the list corresponding to y, then somewhere in this list, you're going to have x. But that's it. So this edge is going to be seen 2 times, once when x is dequeued, once when y is dequeued. And indeed, if you look at the first time one of these is dequeued, like when x gets dequeued, then y is going to enter into the queue. But when y is looking at x is not going to enter the queue, because every vertex enters the queue once when it is visited. Okay, so any questions about that? Good. So every adjacency list gets traversed exactly once. So the total running time of BFS starting from a single source, this is just going to be theta of m, because that's just the number of things in the list. But the total running time of BFS, if you were to do it on G, is going to be theta of m plus n. The reason there is a plus n over there is because you have this additional for loop that goes over all vertices. So remember that what happens here is that what BFS G does is it's going to go through this list. It's doing a for loop on the list, or sorry, on the array of like the head pointers, right? It's like it's kind of like almost traversing a hash table with chaining or so. So BFS of S is going to visit a bunch of these lists, right? Some lists get traversed, and then as you go down this process, we're going to visit all of these lists. So it's M plus the number of pointers, right? Because some of these could be null, then it has to still visit them. So the running time of BFS is this is linear time. So BFS is a highly efficient procedure. Yes, question?
So I assume that the BFS of S is a breadth first search on a point, but doesn't that still give you the whole tree? Like, because every point that you visit, you would then visit the next point, right? So
good, but
what's the difference?
What if you had some vertices that were not connected to S?
Oh, right, okay.
You wouldn't visit those vertices.
Okay, so then follow-up question.
Yes.
If you have a for loop that's checking every single vertex and running BFS on each vertex,
good question.
Wouldn't that be n times m? Because for every point, so why are we adding m and n?
Because we said that if visited is false, if visited is true, we're not going to run BFS. Remember, BFS on G does not run BFS on all vertices. It only does it on the unvisited vertices.
Oh, okay, I got it. So when you do the rest of the vertices, okay, that's clever.
Right? You're not going to see them over and over again.
So it's not like a whole bunch of trees and like they're 99% similar because they all have the same points.
Exactly. Okay, there are reasons for doing that, which is if you wanted the shortest path information from all vertices, then you would do that. Remember, this is just giving you one tree, which gives you shortest path information to the source. So if you cared about all shortest path information, then you would have to do something like what you're saying. You have to do m times n. But BFS on G is only giving you a collection of trees. Is this point clear? Questions? Questions? Teaching over Zoom is a little difficult because I get no visual feedback on whether people understand or not.
So because it's like only checking when the visited vertex is false, that's why the plus comes in instead of the times.
Yeah, so think of it as that's why what happens is it's a plus because, okay, so if you look at this procedure, now we've argued that every list is going to be visited exactly once, right? And every cell is going to be visited exactly once.
Right.
And so that's the m plus n.
Okay.
Because it's like, you're going down this list, you're going down like the array. There's an array of lists. So you're going down the array. And what's going to happen is if you've never seen that list before, you'll traverse it. But if you've actually traversed that list before, you're never going to traverse it again. If you were to step back and look at what is BFS doing with respect to the list, let's say that you didn't think anything about the graph, you're just looking at how memory is being accessed. What you're going to see is that one of these lists gets visited, then another list gets visited, then another list gets visited, so on and so forth, until all the lists are visited and all of these nodes, all of these head pointers are seen. So if you have a bunch of head pointers that are null, you'll still have to go through them. But BFS of S will never visit an isolated vertex. If you start from a single point, let's say you start from S, you're never going to see these isolated vertices ever. But because BFS on the entire graph is going through a for loop, it's going to visit all of those vertices as well. Is that distinction clear?
Yeah. Okay.
I want us to think about it a bit. I mean, so typically in most cases, M is usually M is larger than N. So, but this is, to be formally correct, BFS of G runs in time theta of M plus N, which is linear time. Okay. All right, so shall we move on from BFS? A is yes, we can move on. B is no, I still have some questions to ask. Okay, so I think that it seems that, an overwhelming majority are ready to move on. So let's go ahead and do that. Maybe what I'll do is, so let me poll you again. Do you want me to talk about homework 4? A is yes, talk about homework 4. B is no, move on. All right, so I think the consensus there is quite clear. You would like to hear about homework 4. So let me just pull up homework 4 and then we can discuss more about it. Just give me a second. Okay. Let me just end the poll. All right, everyone sees the PDF file over here. So this is the PDF that you are going to use for your assignment. So this, in my opinion, is the most fun assignment of them all. It's not actually that much to code, but I don't know how many of you have played this game called 6 Degrees of Kevin Bacon. So the idea is this. You need to find a path between two actors. So I'm going to give you, for example, if I gave you Brad Pitt and Rachel McAdams, you find a path between Brad Pitt and Rachel McAdams through movies. So you say Brad Pitt and David Ayer acted together in Fury and Blood Brothers. David Ayer and Jake Gyllenhaal acted together in The Making of the End of Watch. And Jake Gyllenhaal and Rachel McAdams acted together in this movie called Southpaw Inside the Ring. So your job, your code's job is, I'm going to give you these collect pairs of actors. You have to find this path. Okay? So I am giving you a snapshot of movie credit data. Not everything. I've just collected like about, I think, 100,000 movies. So I scraped this data from, it's not IMDb, but IMDb. Sorry for that mistake. And so you can use any data structure you want. You can store it however you want. I don't care. Just do it efficiently. Right? So the way it works is you're going to get this file called cleanedmovielist.txt. Each line of the file is movie with a collection of actors who have acted. Right? And I've made the parsing easy for you. I've basically replaced all the spaces by underscores. So to parse the line, you simply tokenize by spacer. For example, if you look at this movie, which is a classic in my day, which I loved a lot, but I don't know, maybe I'm dating myself by saying this, but there was this movie called Terminator 2 Judgment Day. Was Arnold Schwarzenegger's one of his big famous movies. And so if the actors listed are Arnold Schwarzenegger, Linda Hamilton, Edward Furlong, Robert Patrick, I've removed any actor who hasn't acted too often, right? So this is so that the list of credits is small. This is your data file. So this is the file that you parse. So every line of this file is going to have a line of this form. There may be different movies with the same name. So be careful. Be careful. Each line is a different movie. Even if movies have the same name, each line is a separate movie. Now, what you get is a collection of actors. You get actor 1, actor 2, and then you have to find a shortest path between them. Your output must contain a shortest path between the actors, formatted in exactly the way that I described. So, for example, I actually have one with Frank Sinatra Jr. and Katherine Hagel. I actually have this like long path between them. Okay, your output may be different from mine because there are multiple paths between different movies. You just have to provide one that is correct. This is like the N Queen's assignment, right? So it's all about graphs in BFS. So you're going to get this data. You're going to get this data, and you have to construct the graph from it, and you solve it by doing BFS. So all of these questions, good questions people had asked, like, oh, but how am I going to store the predecessor array? Do I use a hash map? Do I use this? Do I use that? Yes, you have to figure that out yourself. You can do whatever you want. All you need to do is to be able to solve this problem. I will give you a series of pairs of actors and actors. I'll say, Frank Sinatra Jr. and Katherine Hagel, you have to give me a path output in this way. There are more details on how exactly to format, but essentially it's doing breadth first search in this graph called the co-actor network. Co-actor network. And also if the path isn't present, then you have to say not present, and there are a few things that you need to do. Okay, any questions? Questions?
If you use all STL and anything we like for this or not?
You can use whatever you want.
Nice.
You can use whatever you want. You're essentially going to have to build your own graph, store it, and then you run BFS on it. And it's quite fascinating. You'll find a lot. And of course, I didn't give you the entire IMDb data set because then it's not particularly slow, but then it takes some time, and then I don't want the systems to crash. So I have curated it down to a list of 100,000 movies. But you could play this game with all movies. This is an assignment where, again, like every other assignment, but get to it sooner rather than later, so that in some sense, in this case, a lot of the work is in scraping the data and preparing the graph. The actual BFS is not going to be as painful, but you have to kind of scrape the data, make sure that you parse it, make sure you construct the graph. So doing all of these things will take time. think carefully about how you want to store the graph, prepare that data structure, and then work with some small examples initially. You may want to, instead of like dealing with this file, you may want to construct a little graph with just integers, right? Just like integer, like you could say like vertex 1, 2, 3, 4, and run your code on creating a small graph, make sure it's correct, and then you can move on to this big data set, because debugging this is hard. It's like, it's 100,000 movies. There are like, I don't know, maybe tens of thousands of actors, if not more. So you need to be a little careful. Any questions about this? Any questions? Are there actors with the same name? Good question. So assume that all the actor names are unique, right? Because there's no way that given a name, you would know which actor it is. So the name is always unique, but the movie name is not. So the actor names are unique, the movie names might not be. There indeed are examples where there are multiple lines that have the same movie name. So each line is a separate movie. That's the way to think about it. Questions? I don't know. Doesn't this sound like a ton of fun? At least I would have thought it was a ton of. It's a ton of fun. And you can play it. It would most likely have all the actors that you know of, right? So and it's all about doing shortest path. It's all about doing shortest paths. Okay. Any questions about this assignment? Remember, as I said, you use whatever libraries you want. Any libraries, whatever libraries you want.
Is there anything in the instruction that we might miss if we don't read it carefully?
Like the fact that in homework 3 things are repeated?
Right.
No, I think that this is it. There are different movies with the same name. That's about it. I don't think there are any other gotchas other than that. There is something I will say. The chances for resubmitting this assignment are going to be very limited. Like you'll have like 2 or 3 days to do it because it's towards the end of the quarter. Okay? All right.
Wait, do actors appear more than once?
Of course they will, right? Because that's the way that you will connect them.
Okay.
Right, because actors will appear essentially for every movie, they'll appear more than once. I mean, that's the way that you'll find connections. So think about it as the way that you connect, I don't know, in this case, for example, famous names like Katherine Hagel, James Franco, actually Frank Sinatra as well, they will have acted in many different movies. And so for each movie, they're going to appear in the credits. Do not try to construct this path without constructing the graph. So construct the graph and do BFS. That's the way to do it. Right? Okay. So this is somewhat similar to homework 1, where you have like Shakespeare's text, you process all of it, then you actually process the queries. And it's something similar over here. Okay, and feel free to use like unordered map data structures or ordered maps or whatever to store the adjacency lists. You can use hash tables, you can use whatever you want. Okay? All right, if there are no questions, then I'm going to proceed from here. All right. Right. So let us go back to breadth first search. Obviously, I only have 10 minutes left. I don't want to launch into a completely new topic altogether. But what I would like to do is to maybe start the topic for tomorrow. So at this point, we have 3 lectures left. And as I said, the last lecture, I don't teach in it. I open it to questions. Any question that you may have, I just take questions during the entire lecture on anything, related to the course, unrelated to the course. I don't